Okay. I'm not really sure how this thing works, so I'm going to just control this from here. So I'm going to talk about spin alignments around Illustris voids. I kind of already gave this talk in my PhD seminar, and I'm not sure if there's a lot of overlap between the audiences. Probably not. But even so, I would like to delve a little bit deeper into the motivations about why we wanted new methods to study alignments. And I will sacrifice a little bit, because of time, the explanation of why the method works, to give more importance to why we thought we needed a new method. Can you hear me correctly? I'm not sure. I usually have a low voice. Okay. So,
Excellent.
I'm going to delve a little bit into the motivations, not necessarily why spins are important, which I think they are, but especially about the methods. Spins are an interesting subject to study because there's an underlying relationship between them and the matter distribution. And they also put constraints on models of galaxy formation, galaxy evolution, determination of cosmological parameters via weak lensing studies, and a large etc. And also around voids, there's not a clear consensus of whether galaxies have a preferential orientation or not. So why a new method? Every study of this nature provides a sort of, well, they measure the cosines of the angle of the data that we're interested in measuring, and maybe some kind of treatment of this data, but they usually lack a formal description of the analytical framework in which the parameters that they use lie in. And because of that, they rely on Monte Carlo simulations to estimate how significant their findings are. So we wanted to tackle these two aspects with my supervisors. And we think that the main culprit is the uniform distribution. I'll get into that in a bit. So all of these sort of studies have a null hypothesis approach, which is my cosine distribution indistinguishable from a uniform distribution? That's kind of the main the main idea that we're working with. So we have the uniform distribution in the red line here, and what we usually would hope to find is a blue curve scenario or a green curve scenario in which we find excesses in either parallel or perpendicular alignment. But what we usually find is some ambiguous nonsense in the middle, and we can't really know how significant that is. And on top of that, which is what's worse, if you can see, in all of these cases, the mean of the distributions doesn't change all too much. So we think that this is because of the uniform distribution and its properties. So the goal is, wow, you really can't read anything. Okay. The goal is to assess the significance. I'm going to read it for you. Assess the significance of any deviation from the mean of the reference sample. So we want to see if our mean of the data is different from the mean of the reference sample, which is the uniform distribution. And the usual solution is to use Monte Carlo simulations to estimate the significance of our findings. But the problem for us is the properties of the uniform distribution itself. First of all, we have here that the mean of the uniform distribution is given by the median, not the average. So if I'm comparing my average to the mean of the uniform distribution, I'm comparing an average to a median, which is not completely correct. Is that maybe a bit too pedantic to say? Sure, maybe, but even if it is, the standard distribution of the uniform distribution of this distribution, the standard deviation, sorry, if you replace the values, the minimum and maximum values that you would get in a cosine distribution, which is 0 and 1, you have that the mean is 0.5 and the standard deviation is 0.3. So you're comparing a sample, your reference sample, which is what you're comparing it to assess the significance of your findings, has a standard deviation that's of the order of its mean. And that's not great. That's not ideal. So we wanted to maybe propose a solution to improve upon that. And with these motivations in mind, we wrote 2 papers that have been already submitted. You can't read the titles, so I'm sorry. I thought this was more easily readable. But they're in the archive. You can, if you're curious, ask me for the link, and you can read it. But the first paper is about presenting 2 new methods, actually, and developing their theoretical foundation. And we test them, we do et cetera, et cetera. And the second paper is the application of these methods into the Illustris. And this talk kind of covers both, hopefully. So I'm going to very briefly explain the procedure or how our method works. Because we start with the measurement of an angle. Then I'm going to take you through 3 parameters that we came up with, which is beta, eta, and zeta. I'm sorry, I wasn't too creative that day naming the variables, but this is what I have. So this is a sort of a schematic visualization of how the method works. This is supposed to be read clockwise. You can start wherever you like. And what I really want to, for time constraints, I really want to take you to this plot, which should be a lot bigger. Okay. This final variable, zeta, you will see it in plots like this. This is zeta against the normalized distance from the center of the void. And I'm going to teach you how to read this, hopefully. If this zeta value is positive, it means that there is perpendicular alignment. If it's negative, it's parallel alignment. And because it's normalized to the standard deviation, it means that the absolute value of zeta gives you an idea, or actually is the significance of that alignment. So for example, this sample here, which is between 1.2 and 1.3 void radius, has a 2.5 value for zeta. This means that that galaxy sample is aligned perpendicularly to the center of the void with a significance of 2.5 sigma. So this is how you read it. It all starts with this beta parameter, which is defined to be as the ratio of the components of the spin, the perpendicular component over the parallel component. So if it's larger than 1, it means that it's more perpendicularly aligned. If it's lower than 1, it's more parallelly aligned. And we start from there. You might ask, why not just stop there and use beta? The thing is, you could, sure, but we tried to do our homework and we found that the distribution of beta is pathological. This means that none of its moments converge. You could use Monte Carlo simulations to give you an estimate of its mean and standard deviation. And it will give you something. Monte Carlo simulations always give you something. That's why they're so great. But we wanted to have a theoretical underground for the parameters that we use so that we could assess whatever alignment we find in a more significant manner or in a more robust manner, let's say. I should skip this. Yeah, this is in the first paper. You can ask me about it later if you want. But here we just compare the significance, the statistical significance of our parameter zeta with the average of the cosines, and we find that our parameter is more robust and more sensitive to alignments. That's basically what that means. So the data that we use, straight up, I'm going to tell you that it's the Illustris TNG 301, the biggest and most highly resoluted, I'm not sure that's the right adjective, of the Illustris suites. And we identified 82 voids in total.
2 minutes.
2 minutes? Shit, what? We divided the void sample into R voids and S-type voids. And the galaxies, what we did was, because we wanted to navigate a certain parameter of properties of galaxies to see if there's a property of the galaxies that is most strongly correlated to alignment. We navigated through, well, the distance to the center of the void, radial velocity, spin, mass, and sigma phi. In case you're curious, because this is kind of important, I did take into account that spin and mass are interrelated, so I can't classify them independently. I did a joint classification, let's say. And what's important also in this slide is that here we are working with underdense regions, because I'm talking about maybe 1.2 or 1.3 void radius, and you might think, okay, that's outside the void, that's already the universe. It's really not. At 1.4 radius, void radius, for example, here you have the mean of the density profiles is minus 0.75. So even at 1.4, 1.5, it's still very much under dense regions and therefore in expansion. So the results are roughly the following. This is like the entire sample with none of the selections that I mentioned. And we find that, if you remember, positive values meant perpendicular alignment. We have a general trend of the galaxies to be perpendicularly aligned to the void. And here I've shaded in the really dark region below 1 sigma level and light gray below 3 sigma level. So within this region, it means nothing. It's consistent with random behavior. Under the 3 sigma level, it might mean something, and above the 3 sigma level, it definitely means something. So that's what those shaded regions mean. Here we have the classifications for mass, spin, local density, and velocity. The blue curves are high in whatever parameter we're interested in. The orange curves are low for every case. So as you can see, for high mass, we do have a certain boost in the signal of perpendicular alignment, same as with high spin. Surprisingly, for local density, it doesn't make much difference selecting for high or low local density, which means that the alignment seems to be independent of this parameter. And most surprisingly of all, we find a really high signal for perpendicular alignment for low radial velocity galaxies. This was maybe the most surprising result of all. And next step for us was to make cross samples between all of the parameters, all the possible combinations, for example, high radial velocity with low sigma 5 with high spin and low mass, for example. All of those possible combinations. I made a bunch of tables. This, of course, in the paper is expressed in tables. These are, for example, the most general subsamples. For example, this is the total subsample with no selection, and we find that for all voids, we have a zeta value of 4, which is above 3. When we select for high spin, we boost the signal. Low spin, we get nothing. Low mass, we get nothing. High mass, we do boost the signal again. High and low sigma 5, again, kind of makes no difference. And for low velocity, we have the biggest boost of all. And the way you read, this is in the paper, it's a bunch of tables. I wanted to make it a little bit prettier here, but I think I made it even more complicated, all of this. But the way you read this is, for the samples that have high radial velocity, 0% of them are above the 3 sigma level, and 44% of them are, 44% of the low radial velocity have a high sigma level. The ones that are in bold font are the samples that are above 3 sigma, and as you can see here, we have 2 subsamples with low radial velocity that have over 9 sigma significance level for perpendicular alignment. So this is quite a robust finding, let's say. So now that we have analyzed all of the parameters, we compose like the most highly aligned subsample, which is high mass, high spin, and low radial velocity galaxies. And we comprise the same plot as before. And we do see that, especially for R-type voids, we have a high signal, especially in this region of 1.1, 1.2 void radius, to be perpendicularly aligned. And here's, again, to repeat, this is the profile density of the void. It's still very much a void-like region, a subdense region. So I leave you with a bunch of conclusions, but I really just want to highlight that the properties that most highly correlate with perpendicular alignment we find to be high mass, high spin, and low radial velocity. We don't exactly know why the nature of this cinematic phenomenon, but we think this is where I talk to you. Maybe we can exchange ideas. But we have the idea that whatever process makes these galaxies stumble on their way away from the void makes them gain in spin alignment. That's kind of like what we're working with. And yeah, this is me and my supervisors and our emails in case you want to contact for further questions.
Thank you. we have time for a question.
Fede,
Yes.
have you tried another density environment estimator,
Like,
more local? Because you are within a void, so sigma 5 is almost constant.
is,
Almost constant. So why is sigma 5?
we needed some measurement of the local density of the galaxies. We chose sigma 5. We could have chose something else, but because of the nature of the simulation and the resolution, it's actually kind of dense. So we have subsamples that are the most highly aligned subsample is 78,000 galaxies, and more to the point of your question, it's less constant than you might think. But yeah, it's still. But even if in subdense environments, I would have expected that if a galaxy has more companions, let's say, it would affect their alignment. But it seems that it doesn't. So
But maybe try with a closer companion.
a closer one?
Yes.
I don't think so. Maybe not.
Yes. Some significant.
I haven't checked. I don't think so. I mean, as much as absolute values go, I don't think it's going to be the same as in a cluster, for example. Right.
Okay. Is there any other question? If there is not, let's thank again to all the speakers for their wonderful talks. And coffee break.